So what we are going to do today is how to do Masonry micromodeling with STKO and OpenSys. So how to do it with the tools that we have in OpenSys. So just a brief introduction. You know very well that Masonry can be modeled in many different ways, and micromodeling is one of them. Micromodeling is especially used when you want to do detailed analysis on small pieces of the structure, because of course you need to model the entire microstructure, so bricks and mortar joints. Here I will show you how you can do it quite easily with a user interface and with a constitutive model that we have implemented in our own version of OpenSys. So if you downloaded STKO plus OpenSys, the OpenSys version that you have there has an additional constitutive model for concrete and masonry that is quite effective and quite robust because it uses a particular integration algorithm that basically makes the model quite always converge. We have a message here, let me see. Okay, perfect. So, and this one is the example that we are going to do. Let me show you the reference. I took this example from the PhD thesis of Oliveira. Well, this PhD thesis was focused on the cyclic behavior of blocky masonry structures. So this is what we are going to do. This is the reference. The model is this one. So it's made of bricks and mortar joints. These are the dimensions for the bricks that we are going to put here. We are going to do a 2D analysis. This is the entire thickness. And this is the dimension of the wall. So we are going to model the entire structure, and then we are going to model 2 steel beams on the bottom and on the top. Then we are going to apply first a vertical displacement. Then I will show you how to apply a fixed rotation at the top beam when you are dealing only with 2 degrees of freedom displacements in UX and UY. And then in the second stage of the analysis, we are going to apply an imposed cyclic displacement on the top beam. Here, always from this reference, you can get all the material properties. In this case, the material properties has been used for the interface elements, because in this model they are using interface elements. But I already converted these parameters into equivalent continuum one, because in our case we're going to use continuum models, both for the bricks and for the mortar joints, as you can see here. So mortar joints here are physically modeled with the finite thickness of 10 millimeters. And basically the output that we are going to get, let me move this one away. Okay, here it's fine. So this is the output that we are going to get. Let me just show you how it behaves. Here we are looking at the tensile damage pattern. So these are the first cycles. Oh, let me go a little bit faster. Okay. As you can see here, you obtain the exact failure pattern we are going to see in the reference. And here, you can, of course, you can extract the results in terms of top displacement and reaction force, and then we are going to plot everything onto the reference model here. Okay. So these are the final results we are going to get. So we can get started. Now let me start a new file. Okay, and then we start a new file here. Perfect. So the first thing we are going to do is to do the geometry of the model. So here, as I told you, we have all the dimension. So first of all, we are going to model just one of those bricks using these dimensions. Of course, 2050 and 120 is the actual thickness of one wall, or one layer. But the entire wall is made of 2 layers, plus 10 millimeters of mortar joint in the open direction, so the total thickness will be this one. So let's start modeling a simple brick. In this case, we are going to stay in the XY plane, because every time you do a 2D analysis, you need to stay in the XY plane. Otherwise, OpenSys will complain about the orientation. So we can start with a planar face. So we click this one, and we start from the 0 coordinate. Then we go on the right of 2050. I'm going to type 2050 millimeters on the input bar. Press Enter. And then 55. Then we go back 2050. And we are done with just one of them, okay? Now, let me model, let me do a couple of things actually. In this case, as you can see from the drawing, this kind of pattern can be quite difficult to model. So I'm going to create some construction lines to make my life easier in this case. Okay, so let me move this one on the right, about half of the mortar thickness, so 5 millimeters. Okay, I'm going to do some construction lines here. Okay, let's say actually I don't need this one. I'm going to do it in a different way. So let me take this one, let me copy it. Half of the mortar thickness, so 5 millimeters. Then the brick thickness, 250, sorry. And then other half of the mortar joints, so other 5. Okay. Why I'm doing this? Because I need to create the other the other bricks on the top, and they are based on these dimensions. So let me draw a line here. Let me copy this one, 55 on the top. And then let me do some other lines, starting from the middle. And then I want to divide this one into 2 parts. So let me create another line here. Okay, so that I can do this. Then I will explain you why, just to create a regular pattern. Line here, and let me do it again here. So I draw another line here, so I can get the midpoint. Perfect. So now what we're going to do here, as you can see from the drawing, basically we have, for every 2 bricks, we have 5 of these modules here, and then a small one on the other side, which is half of this one. So let me go back here. Let me copy this one, 10 millimeters on top, and then another 55, which is the height of the brick. And then we have this one. Now we can copy these 5 millimeters here, which is half of the thickness of the mortar. And then we do the same with this other line. Perfect. So why am I doing this? Because now I can join everything with the merge command. Merge command will basically join all the lines, creating the intersection. So I get the construction points. So I click merge. Then it says, select all the geometry you want to merge, and I want to merge everything. Right click, and then I have just one geometry now with all the intersection points. Perfect. Now what I can do is to create the faces. One for the bottom brick here, so the full module. Oops, I took the wrong Osmo point. Let me do it again. Here, 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 and back. Okay. And then let me do the other one here. So I get all the correct dimensions. Perfect. Now I can remove my construction lines. So these are 2 modules. Now Let me see how many of them we have on the bottom. We have 2 of them plus the remaining. Actually, the remaining should be cut, otherwise they don't fit in 1 meter. So let me copy this one. I go here, and then I move it 10 millimeters. And then I do the same on the other side. Now from here to here, so I already have the 10 millimeters. And then let me copy them again. From here, here. And once again, this one. So now, as you can see, they are slightly more. Let me see how many of them we have. Actually, we only need 4 of them. Actually, let me see. Yes, 4 of them. So let me remove this one. Now let me move everything. Let me center everything. So let me create a line here. I want to put everything in the center. So let's take everything, move, and then move this one at 0, 0, 0 coordinates of the center. Perfect. Now, as you can see, we have an extra part here that we need to cut because it needs, the last module is not full. So here and here. So we have the 1 meter total width of the wall. How do we cut them? We use the merge command. We merge these 2, and then we do the same here. Okay, now we can get, now we want to remove this line. As you can see now, they have been merged. But in this way, I can remove this face here. So I remove the selection of the entire geometry so that I can select the sub-geometry, and I click on this one, and also this one and this one, and I press cancel. So I can remove those. Now the entire thickness on my wall, on the entire width, sorry, is 1 meter, exactly as in the drawing here. Okay. Okay. So now we can start copying this. So let me take the copy command. Let me copy this one from here to here. Now let me move this one 10 millimeters. Okay, and now we can start copying them. Now we need actually how many? Let me see. We need 5 of them. So copy from here to here. Then once again from here to here. And the last one, which is here. Now the next 2 modules, as you can see from the drawing, are exactly 1/2 of this one. So let me copy these here. Now let me divide it in 2. So I draw a line in the middle, but then I need to include half of the thickness. So I get the copy, or actually the move is sufficient. I select this line, and I move it. Let me look there. Okay, right click, and then I move it on the right of 5 millimeters. Perfect. Now I need to cut them. So I click merge, and I select both the face and the line. Right click. Once again, as before, I uncheck the select the entire geometry, so I can select this small face here, and I press cancel. Perfect. And now I can go back to the entire selection, and I copy this one on the other side. And now let me move it 10 millimeters. Perfect. Now we need the last module. Now this is actually the most annoying part because then we can copy everything. So the last one, let me copy this from here to here, and we need to cut a little bit. I select everything, I click merge as before. Okay, go under sub-selection, and I remove this line, this extra face, and there's a construction line. right click. Oh, I need to click cancel, perfect. And now I can copy this one. And we are done with the first module of bricks. So copy. Then once again I select it and I move it 10 millimeters. Perfect. Now we are done with the first layer of bricks. Now we need to create the mortar joints. Now before doing everything, I will create some physical properties, which are the material models. Actually, I can do it later, but when you do micromodeling, it's easier to assign the material model before, because when you copy the other geometries, the material assignment will be copied as well, so it will be easier. Now, let me just create two material models without specifying any material parameter. They are just used to create the assignments. So let's create a material model for the brick. Let's call it material ND. At the moment, it is not necessary. We choose just a linear elastic one. Then we will change it. There is no need to assign parameters because it will be changed. And then let me copy once again this one, and we do the same for the mortar. Okay, and let's call it mortar. Okay. Now, as you can see, we go under property. Now they are transparent, but we can select all of them. They are bricks, so we can just drag and drop the brick one. So as you can see now, they get the color, default color that we have on the brick. Now we need to draw the surfaces for the mortar layers. So let's go back to the geometry. And let me create a 4-point face here. Okay, now I go on property. As you can see, this is transparent, but I can select it and I can assign the mortar material. Okay, why? Now we can copy this one, and you can see that the assignment will remain. Now I can go either here, edit, copy, or I can just type the command like this, copy. Now let me click here and let's start copying it. Okay, here, here. Here on the bottom. As you can see now, they already have the material assignment. That's why I did it before. Now we need an extra layer here of mortar joints. So let's go back to the geometry and let's create a face 3-4 that goes from this point all the way to the other side. And let's close it like this. Go on property, select it, and we assign the mortar material also to this one. Perfect. Now, as you can see, they are all detached. We need to do some extra operation now. Why? Because if we attach everything with the Boolean operation, then we are going to have some surfaces like this one or this one that have more than 4 corner points. So they are not suitable for structured mesh. So I typically want to do a structured mesh. So what I do now is to create construction lines to create cuts here, here, so that all the faces are 4-noded. In this way, it will be easier to do a quadrilateral structured mesh. So I go on geometry and I start creating construction lines from here down to the bottom, and then I click this one and I copy it. Okay. So they will be used to create cuts in such a way that all the surfaces are perfectly quadrilateral shaped. This is not mandatory, but it is better for a good meshing. Here, and then let me do the same on the top. Here, here, and a few others. And also here, and we are done. Okay. Now what we can do is to create a merge command, and we attach everything. So we select everything, right click. What we obtain now is a single shell, as you can see, and the material property remains. But what's the difference? Now we have divided the brick into sections in such a way that every face has exactly 4 corners and 4 edges. So they would be suitable for quadrilateral structure mesh. So now this is fine. We just need to copy this face down so that we have a module that can be repeated. Okay. So let me copy this surface, or actually instead of copying it, I can use another geometry command that I will show you, which is the exclusion, and I can click on extrude. Now the extrude command can extrude everything. Actually, what I want to do is to extrude lines into surfaces. So I unselect everything except the lines, so that I can select like these only lines, right click, and then I go down of 10 millimeters. Right click, perfect. I go back to the property, I click on this one, and I assign the mortar material. And once again, I select everything, and I type the merge command. And I want to merge everything, perfect. So now what we have is exactly one module that can be repeated. So if we go on the drawing here, we need to repeat this one 10 times, and then we need to add an extra layer that finishes with the same one as the beginning. So let's go back here, let's select everything, and let's copy. Let me type copy. Okay. Three, four, 5. Now we are 5, so we can select everything, and once again, copy. So we have 10 of them, I think. Let me see. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Perfect. Now we need to copy the last one once again. Like this. And we need to remove just the last line. So let me go and uncheck this one. Let me select this face and press cancel. Perfect. So now we have, if you switch off the visualization of points and lines, you can see that what we have is exactly the geometry that we want to reproduce here. Okay. So let me switch it on again. So what we can do now is to select everything and do a final merge. Let's type merge. And we want to merge everything, perfect. So what we have now is just one single face. And actually, it is a polysurface, so a series of faces connected together. So before going ahead, let me save it. Let me create another folder here. Let's call it shear wall. Let's go here and let's call this model shear wall. Okay. So the last thing that we need from the geometrical point of view is to create the steel beams. Now the height of the steel beams is not so important, I think 80 millimeters. So we can go under geometry, we can use the same command that we used before, the extrude. Once again, we want only to extrude lines into surfaces, so we switch off everything but lines, and we select all the bottom lines, right click, and then we go down, let's say 80 units, right click, and we copy this one, copy, on the top. Okay. Now if we go on property, we can see they are transparent because we didn't assign anything to this one. So we create another physical property for the steel. Let's call it steel. In this case, it will be actually a linear elastic one. So we go under other ND materials, elastic isotropic. And let's give, by the way, I'm modeling in Newton and millimeters. So this These are the units. 25, okay. I select this one, and I drag and drop the steel material model. Okay, now that we are fine, we finally join everything into a final merge. Okay. So now our geometric model is completely done. Let's save it again. Now we can start assigning physical property. As I told you before, brick and mortar, only the steel has the real material properties. Brick and mortar joint were just placeholder because it was easier to assign than before copying everything. Now we can start assigning material model. Now we need to do a couple of steps. First of all, let's create the brick in this model, brick and mortar should be 2D materials. Now, actually, the material that I'm going to show you is a three-dimensional one. So we need to transform it to 2D later on. So let me first create another material model, which is called brick 3D. And we are going to choose a material model under the ND material as their software in the damage TC 3D. So I'm going to show you the parameters for this one. As I told you, the parameters were taken from this slide of this slide here, if you want to go on the reference. And these are the parameters that I have here for bricks and for mortar. So let me type them. I have them here. Okay, so the brick one has a Young modulus of 2,500 megapascal. And then a Poisson ratio of 0.15. Then we have the tensile strength of 1.2 megapascal and the fracture energy of 0.002. Then we have this one is the tensile behavior. Now we need to define the compressive behavior. Here we have the compressive elastic limit. In this case, it was 20. And then the peak compressive strength was 26. And this one is a residual compressive strength of 1 megapascal. This one is the compressive strain at peak strength. In this example, it is 0.02. Make sure that this value divided by the Young modulus should be less than this one. Otherwise, the compressive model will not work. Then we have the compressive fracture energy. In this case, it's 2. Then these parameters are not important. You can leave the default ones because they are just used to shape the compressive surface. I will show you later on. Then these are the miscellaneous commands that I use basically to define the three-dimensional behavior. You can leave it as the default one. I will just these two parameters can be changed because they define how the model should behave in terms of damage and plasticity. Now in this case, for the brick, we want to use pure damage, as you can see here. So we put 0 and 0. Instead, 1 and 1 will be full plasticity, and something in between will be something in between damage and plasticity. Now, finally, here you have the integration method. By default, it is implicit. Otherwise, you can use the implex. Now, the difference is that the implicit one, as you may know very well, with the implicit one, you can use the time step that can be as large as you want. But of course, the solution will be highly nonlinear. While with the implex one, it will be a mix of explicit and implicit integration algorithm, so that the convergence will be much better. So we will use the implex one in this example. Now, let's say we want to see how these parameters are working. We can do it with the material testing. So if you are not sure about how they behave, you can do some tests. Let's start with a monotonic test in tension. So let's choose 1000 subdivisions, and let's push this one up to a tension of 0.05, for example, in the x direction. So let's test it. So this is the behavior in tension. And let's say, okay, this is fine. So let's test it also in compression. 0.02 is the peak. Let's see. As you can see here, it arrives up to the peak. Let's push it a little bit more. Let's say up to 1, so we can see how it behaves in the post-peak. Okay. If we push it even more, we will see that it reaches the FCR, which is the residual strength. So let's push it other 3 times this one. Okay, so this is the entire behavior in compression. And then, of course, we can do some tests also to the other components, but it is not necessary now. And if you want to see how it behaves in cyclic behavior, let's see, let's put 1000 subdivisions. Let's put here the peak compressive deformation, which is 0.02. Let's do a test. Okay, so this is the cyclic behavior of bricks, and as you can see, the unloading modulus is the second one because we used full damage in both cases. On the other hand, if we put, for example, 1 and 1, which is full plasticity, the unloading modulus will be exactly as the elastic one, as you can see here in this case. And of course, you can choose something in between, for example, pure damage in tension and pure plasticity in compression, and you will have this one instead. Okay, or something in between, like, for example, 0.5. Now it will be half plasticity and half damage, and you will have something like this. Okay, so in this example, for the bricks, it is sufficient to use pure damage, so this one will be enough. So let's press OK. Now let's move the brick up, because as I told you, this one is a 3-dimensional constitutive model, but the elements that we are going to use here are plane stress in 2D. So what we need to do, this one is a material model that we assigned here. We right-click, and we want to use for those ones an ND material, other ND material, plane stress, that is actually transforming a 3-dimensional model into a plane stress one. So we want to transform the brick 3D into a plane stress brick. We press OK. So what we have done here is to use a 3D model for the bricks, convert it to plane stress, and the plane stress has been assigned to the bricks actually. So we do the same for mortar. Let's create another one, and let's call it Mortar 3D. Once again, we go under material, ND as the software, damage TC. Okay, so for the mortar, we have 400 megapascal, Young modulus, 0.15 the Poisson ratio, then we have 0.15 tensile strength, and 0.004, which is the fracture energy. And for compression, same meaning as before. So 3 is the elastic limit, then we have a peak strength of 5, and then we have a residual strength of 2. Now the peak strain is 0.03, and our fracture energy here is quite high, like 8. Now in this case, we are going to change the shape of the tensile surface into a lublinar one, because this one gives a better performance for shear for mortar joints. I'm going to give you a reference paper where all these parameters are well explained. It will be in the folder that we will share on our website. So I'm not going to waste too much time on this now. Then what we have, we change the integration method into implex as we did before. And in this case, here, yes, we need to put some plasticity for the mortar joints. Otherwise, the cyclic behavior will not be so good. So we use 0.4 in tension, 0.7 in compression. So let's test it. Let's see what happens. So okay, let's do a cyclic test now. 0.03 was the peak. So this one is the behavior in compression and tension. You may see that there is slight plasticity both in tension and in compression. Okay. So we move it up because it should be defined before this one. Otherwise, this one cannot be converted into a plane stress. So let me move it up to the mortar. And then, as I told you, as we did before, we convert the mortar that we defined before into a plane stress adapter. So we go under ND material, we choose plane stress, and we choose as the 3-dimensional model the mortar 3D. Perfect. So now we are fine with the material models. We have a two-dimensional brick here, two-dimensional mortar here, and then we have the steel model. We are fine, let's save it. Now we need to define the next thing, which are the element properties. So these are two important things in STKO. Physical properties actually means the constitutive behavior of your geometry here. So materials, section, and so on. But actually this is not sufficient. In OpenSys you need to assign both a material model that defines the constitutive behavior, and then you need to choose a finite element model that defines the kinematics, let's say. So in this case, we want to model everything with a plane stress quadrilateral element. So we go here, we choose add, let's call it quad, and we're going to choose one among the quadrilateral elements in 2D, and we choose the standard quad, so fully integrated standard quadrilateral elements. The thickness of the entire wall is 250, and then we are doing this model in plane stress, not plane strain. So we change it to plane stress, we select everything, and we drag and drop the finite element. Okay, so now we define the geometry, the constitutive behavior, and the kinematic behavior. So we have everything. Now we need to go under conditions. Now we need to start defining and assigning the boundary conditions. So in this example, what we have is actually a fixity at the base. Then we have a vertical load of 150 kilonewtons total. And then we have a constraint that basically avoids the rotation of this beam. So the entire beam cannot rotate, can only move up and down or left to right of the same quantity. So how do we do all of this? So the first thing that we're going to do, well, let's move to the condition tab so that we can see the boundary conditions. We go under condition, right click, add. The first one will be the fixed base condition. So we go under model, constraints, single point constraints, and we use the fix command. We are in 2D, we are using only displacement degrees of freedom, so we have only 2 degrees of freedom, and we fix both of them. Now before clicking OK, as you can see here on the command prompt, you need to select all the geometries that which condition will act on. So we're going to select everything on the bottom line. Okay. So now this condition is at the bottom, as you can see. Now the next condition will be a vertical load up here. So right click, add, and let's call it vertical load. And it will be this time a load, and it will be a force. Now, as you know, in OpenSys, you either have distributed load only under the command LA load, but unfortunately this command is only available for beams. Now in this case we are not using beams, we are using continuum elements. So what we have in OpenSys actually is just plain nodal loads. But fortunately in STKO we created some automations. As you can see here you have edge force or face force. And you may ask, okay, but OpenSys doesn't have distributed edge force on surfaces. Yes, but in STKO we did it in the sense that the user inputs a distributed load over an edge, and then STKO does the nodal lumping automatically, so that the TCOL file in OpenSys will have a lot of equivalent nodal loads. So this is quite convenient. So we choose edge force, and now we need to create a total force here, which is by the reference there, 150 kilonewtons, but we are working in newtons, so we need to type 150,000, but we need to divide to the total length, which is 1,000. So the total value that you apply here is 150 newtons per unit length, so every millimeter in this sense. Let's make it negative. Let's press OK, and let's select all the edges on the top. Okay. And as you can see here, we have this distributed load pointing downwards. Okay. Now the next boundary condition that we need to assign is a boundary condition that fixes the rotation of the top beam. So the beam cannot rotate, can only move as a shear wall. And how do we do this? we need to create an equal dot constraint. But before doing this, we need an interaction. So we go back to the geometry, and we go under interaction here, right click. Let's create an interaction. So add. Let's keep the default. Let's just change the name and call it fixed rotation. And we choose a node-to-node link, which is fine by default. Okay. As you can see here, STKO asks you to select master geometries. So we want to select the master node here, right click, and then all the slave geometries, which are all the lines on this level, right click. As you can see here, this one creates a series of connections from each slave point on the line to the master node. So we can use this interaction to create the next boundary condition here. So we go under condition, and we create an add. Let's call it fixed rotation. We go under model. This time we choose constraint, multi-point constraint, because we want to constrain a slave degrees of freedom to a master degree of freedom. And we choose an equal DOF. We are in 2D, just displacement is fine, and we check both of them. Why? When we check the Y direction, basically this one will prevent the rotation of the top beam, because all the nodes of the top beam can displace in the vertical direction of the same amount. So basically it cannot rotate. And then we need this other one, because in the experimental setup, the entire beam is forced to move in the same amount in the horizontal direction. So before pressing OK, we need to select the interaction. This condition we act on, and we press OK. So now we have also this boundary condition applied on this interaction. Now the final boundary condition that we need is the imposed displacement. Now we can impose this displacement only to this point, because it's the master, so all the nodes will move of the same amount. So let's go under condition, add, and let's call it imposed displacement. An imposed displacement in OpenSeas is actually a load. So we go under load, single point load, and we apply this one, which is the prescribed nodal value. We are in 2D, only displacement, and we want to apply a displacement. Now, for the x value, we're just going to put 1 as a reference value, because the actual value will be assigned through the time series. So let's put just 1, and let's select the target. The target for me should be this node, the master node of this kinematic constraint. And press OK. Perfect. Now we have all the boundary condition defined. Now, the last thing that we need to do is to create all the analysis steps for our analysis. Now, before doing this, let me save it. And let me create a couple of more things. We need to create some time series, okay? Because we will need them to define how the vertical load and the imposed displacement will evolve during the analysis. So the vertical load will be applied in a linear increasing fashion. So we just need a linear ramp. So let's call this one linear. And let's choose a time series which is linear. So this is perfect for now, from 0 to 1. And press OK. This is fine that we put this one from 0 to 1, because the reference value of the vertical load is the actual reference value. So the time series should go from 0 to 1. Now, on the other end, the imposed displacement has a reference value of 1. So we will apply the total displacement in the path time series. Why? Because we have the values from the reference. Okay, let's call it cyclic. We go under time series and we choose the path. Here we are fine. We just go under list of values. We go here, we edit, and we need 20 points. And you will discover why. We need 20 points, and I'm going to take the points from the reference paper, which are these ones, as you can see here. So we're going to do 2 cycles up and down at 1.5 millimeter, then other 2 cycles up and down at 3, same at 4.5, at 6. At 6, actually, we're going to do 3 of them, and then 1 at 7, we go back, actually this is 7.5, 7.5, and then we go back to 0. Okay, so let me go here, and let's put it 0 at the beginning, then we have 1.5, minus 1.5, once again 1.5, and minus 1.5. Then we have other two cycles at 3, so 3, minus 3, 3 and minus 3, then 4.5, minus 4.5, once again 4.5, minus 4.5, and let me remember, I think 3 of them, yes, 3 of them. So once again 4.5 and minus 4.5. Then we have a 7, not 6, sorry. No, I made a mistake actually. There were 2 at 4 and 3 at 6, okay. So this one is actually 1, 2, okay. 6, minus 6, 6, minus 6. Then we have once again another one at 6, minus 6. Then we need a few more. So 1, 2, 3. Then we need 7.5 minus 7.5, and then we go back to 0. Let me check it. Yes. So we are fine. 22. Okay. Let's press OK. And then we need to choose a value here, which should be 1 second total divided by 21 points, which is 0.4476. 0.0476. Okay, so the total amount of the analysis will be up to 1. Okay, so this is our cycle. So let me create a little bit more room here, as you can see. Okay, perfect. Let me save it. So now we can start creating all the analysis steps. This is very important because up to here, what we have done is to create our model, to assign the constitutive models and the finite element formulation, and then we created and assigned the boundary condition. As you can see, they have just been defined. The boundary condition, they should be defined, but then you need to specify when to apply them in the analysis steps. So here, everything we will define in the analysis steps. Their order will be extremely important because the order in which you put analysis step is the same order in which that command will appear in the OpenC script file. So the first thing that I want to do here is to assign boundary conditions. Is to actually to apply boundary condition. So the first boundary condition that we want to apply are the fixed constraint and the kinematic constraint for the top peak. So let's call these add conditions. So we go under model, we go under patterns because condition and loads should be added as patterns. So in this case, we want to add a pattern, otherwise we can remove a pattern. In this case, we want to add it, and we want to add a constraint pattern. So we click on this one, and here we can assign, we can put here all the single point constraints in this vector and all the multi-point constraints in this other vector. Now here we have just one single point, which is the fixed base, and one multi-point, which is the fixed rotation. So I go here, I make room for one, and I choose fixed base. And then I go under multi-point constraint, I make room for one, and I choose the fixed rotation. Okay? So we press OK. And OK here. So the first analysis step will write all the boundary conditions. We'll apply the fixed at the base and the kinematic constraint since from the very beginning of the model. Then the second step is to apply the vertical load. So let's go under add. Let's call this add vertical load. Let's go under model. Once again, a load as for the condition should be assigned using a pattern. So we go under pattern, but this time we choose a load pattern, which is a little bit different than the constraint pattern. When we choose the load pattern, As before, we have many vectors here where we can assign the different loads. Now, in this case, we have only one kind of load, which is called vertical load, and goes into this vector here. So we make room for one, and we choose vertical load. Okay? But we also need to choose the time series. Now, in this case, the vertical load should be applied in a linear increasing fashion, so we use the linear time series. And we press OK. Now, the next step, now as you can see here, we applied the fixity, the multi-point constraint for the fixed rotation of the top beam, and the vertical load. We didn't apply the imposed displacement. Why? This one will be done in a subsequent step. Now we need to do the vertical analysis. So we go under Analysis step, Add, and we call this one Vertical Analysis. We go under Model, Analysis, and Analysis Command. So the analysis here is static, even if we are doing a cyclic analysis, but it is still cyclic. By default, the constraint handler. The constraint handler by default is plane constraints. Unfortunately, we cannot use the plane constraint in this model because we are using an imposed displacement. So what we're going to use is the most general one, which is the penalty method. And we can leave the default values as this one, 1 to the power of 18. The number is fine, this one by default. Also, the default system is fine, the UMF pack. Now, in this case, we're going to use, instead of the Newton method, we're going to use the Krylov Newton, just because we want to make it a little bit faster. So we tell the Krylov Newton to update the tangent matrix every, let's say, 100 iteration, just to make this one use the tangent matrix only at the beginning of every step. Now, this one instead is very important. By default, we have this is the convergency test. By default, we have a test on the unbalanced force, so on the residual. Unfortunately, when you use the penalty method, you cannot use a convergence test based on the residual vector. You need to use a convergency test based on the solution vector, so either the displacement increment or the relative displacement increment. So in this case, we choose the displacement increment test. Why you cannot use the residual vector? Because the penalty constraints are actually adding the reaction forces as forces on the residual vector, so they will never go to zero. That's why. So let's choose a non-displacement increment test. Let's choose 1 to the -5 as a tolerance. And let's put here, let's say, 100 iteration, even if we will never reach so many iterations. And we also want to print them. We just want to print the convergency, so we see if the model has some problems. And for the first analysis, so the vertical analysis, just 10 time steps at a lambda of 0.1 is sufficient. So at the end of this analysis, we want to keep the vertical load constant, and we want to reset the time step to 0, so that we can start with the second time series here. We press OK. Now, up to here, we are ready for the first analysis. Then, after the vertical analysis, we want to apply the imposed displacement for the horizontal analysis. So we go under Add, and we choose Add Horizontal Load. As before, we go under Pattern, we choose Add Pattern, and we choose Load Pattern. This time, the horizontal load is not actually a load, but it is a single point constraint. So we go under this vector here. We make room for 1 because we have just one constraint of this kind. And we choose the imposed displacement condition that we defined before, as you can see here. We press OK. And now we need to choose the time series. The time series will be the cyclic one. Okay? Let's press OK. So we have the vertical load. And now we can do the horizontal analysis. Now the settings will be very similar to this one. So instead of creating a new one, we can just right-click on the previous analysis and click Clone. And now we're going to edit just the small differences. So everything is fine like this. Let me just change the name from vertical analysis to horizontal analysis. And then let me do just a change here. We don't need to put the load constant because in either case, this one will be the last analysis. And we're going to use 1 to the minus 3 increment, and we want to use 1,000 increment. So basically, we do 1,000 steps at 1 to the minus 3 delta increment, so that at the end of this analysis, we will reach a time step of 1, so the complete time series for the cyclic load. And let's press OK. Now we are done here, but as you can see, we didn't put the recorder. Now we need to put the recorder, actually. Why I didn't put it before? Because I want to record only the last analysis. So let me create the recorder command. Let me do a recorders and PCO recorder. So let's call these results. And I want to record displacement. Oh, sorry. Displacement, reaction forces. So we can plot the load displacement curve. And then I want to record something on the elements. For example, I would like to record the stresses and strain at every integration point. But I also want to record something. My material model here, the damage TC3D, has some other output variables which is not listed here. So whenever you want to record some variables which is not available under the default ones like stress, strain, force, and deformation, you can always do it here. So my variable is actually damage. The damage is the tensile and compressive damage. So you can use the custom command. Let me make room for just one. And I want to record the damage at every integration point. So it is sufficient to write material dot damage. Now damage is the name of the results. And before I write material dot, because this one means I want to record the damage variable on every integration point of these 2D elements, pretty much like material strain and material stress. So let me press OK and do OK. Perfect. Now we need to do something here. I need to put the recorder just before the horizontal analysis. Otherwise, this recorder will never be called. Now, if I place the recorder here, my recorder will only record the horizontal analysis. If you also want to include the vertical one, you need to move it up before the vertical analysis. Now, to the end of this example, we just need the output for the horizontal analysis, so here it is fine. So let me save it. Now, the last thing that we need to do is to create a mesh. Now, here, the best thing would be to use a mesh size with the same height of the mortar joint thickness. But here we want to make things faster, and the results will be good anyway. So we're going to choose a global seed, uniform by size of 30 millimeters. Let's press assign. As you can see, this one will be the dimension. Now, even if the elements here will be slightly rectangular, it is not important because the micromodelling in every case will recognize that the crack pattern should follow the mortar layers. So it is not so important to have a regular mesh. So this one is fine. Let's press done. And now we want to change the element type. By default, the element is triangular, but we need the quadrilateral one, because it should be compatible with the finite element we choose here. So we go under Mesh Controls, we go under Faces, we select all the faces, okay, and we choose for those faces a structured mesh algorithm, and the topology should be quadrilateral or hexahedral for 3-dimensional. The order, it is fine linear, otherwise we have quadratic, but in this case in OpenSys we don't have quadratic to the elements for the plane stress model. So linear is fine, assign, done. Perfect. Now we just need to build the mesh. Don't forget to build the mesh, because otherwise you will have problems when you run your model. So just build mesh. And this is our final mesh, okay? So there are not so many elements, 6,000, almost 5,000 elements, 7,000 elements. So let's save it. And we can run the analysis now. So now you can either just write the input file or directly run the analysis. Okay, so let's run it here. Okay, So as you can see here, it starts iterating, it is fine. And then the pushover analysis. Now actually, this one will take something like 10 minutes to complete. Now it is not important to do it now, I press cancel, okay, because I already have the results. But let's say in 10 minutes, this analysis is done. So when you have the results, now you can just open a database. And this one was the one that I already ran. So for the entire analysis, it takes almost 1 gigabyte of results. So open it. Okay, by default, when you open it, it creates the default plot, which is the default shape. I want to delete this one because I want to see the surface color map. Okay. And once again, by default, the surface color map shows the displacement. So let's see first the displacement. Let's make a deformation scale of 10, or actually 20 should be fine. And let's try to do an animation to see what happens. So this is what is happening. From the displacement, you can see the displacement jump here. So you can see the formation of the graph actually. Okay. But probably it is better to visualize other results. So this one is the displacement. You can go here, you can change. For example, some significant results can be material damage. The material damage is actually, let me switch off the mesh edges so the, okay, this output will be better. Now some note about the damage. The damage variable, actually the damage results is made of 2 components, the tensile damage and the compressive damage. Now, typically what you want to see is the tensile damage. Anyway, the damage variable is a variable that goes from 0 to 1. 0 means the material is still elastic. 1 means the material has lost completely the load-bearing capacity. So you may ask, why do I have a damage variable here which is more than 1 and here which is less than 1? Well, this is just because the Gauss points are internal to the element. So when you do the extrapolation to the nodes, it may happen that if you have a damage variable here of 1 and here of 0, when you do a linear extrapolation, it becomes more than 1 and less than 0. But instead, if, for example, if you visualize the Gauss points, you will see that the damage variable, let me go under damage, goes exactly from 0 to 1, as you can see here. Because now we are looking at the real results inside the Gauss points, okay? But of course, visualizing the surface plot is kind of more appealing. So I go on the surface, and if you want to visualize the damage, what I typically do is I choose damage, and to avoid the fact that here I see damage which is higher than 1 or less than 0, I fix a user minimum of 0 and a user max of 1. So I clamp those values. And for the damage, I typically choose the hot color bar. So it's easier to visualize. Now let me put 20. Now the damage variable is actually something that represents the non-reversible process of the material model. So the damage variable will only grow. So as in this case, for example. When the damage appears, it will never go back to 0. It can only increase, as you can see in this case. So it's fine to visualize the final crack pattern, but if you want to see, like in a cyclic analysis, what is the actual crack that is open, probably the damage is not the best variable. You can use something different. For example, the maximum tensile strain. So you can go under here, principal max, and let's say, now, don't put a limit to this one, okay? Let's see what happens. So you see, in this case, you see a crack, the opening of the crack actually, and also is reclosing. So at the beginning, you can see that the main cracks, well, actually at the beginning when everything is elastic, the strain is almost uniform. Then you have localization at the top and bottom toes. And then only at a later stage of the analysis, you see the diagonal cracks in the middle. Up to a final failure of the model when the crack reaches the corner here. Okay, so let's go back to the damage. Now what you can do here then, if you want to visualize what's going on, so the crack pattern is fine with the output results. Let me see if I saved an image of the results. No, I didn't save it, so let me open the reference model so you can see the crack pattern of the experiment. It was, chapter 6. It should be chapter 6, a little bit forward. Okay, so this one is the regular wall, and then this one is the one that we analyzed. And also here, the crack pattern they obtained is the same. This one is the high wall, and this one is the low wall. This one here. As you can see, everything starts with tensile cracks at the beginning, and then you have an almost vertical diagonal crack that coalesce with the corners just at the end of the analysis. As in this case, well, in this example, they had convergence problems at this point. Let me show you. So this is the monotonic response. This is the tensile response of the experiment, but here they had a sudden drop at this point, so they couldn't go forward. The nice thing about the Implex model instead is that you can go up to the end without convergence problems. And so let's see what happens if I extract the results. So what you can do now is to extract some data to post-process it, for example, in Excel. So the first thing that I want to do is to extract the top displacement at this node. So I go under choose result type, I choose the nodes, go to next, then I choose the stage, which is only one, the last one, and I choose displacement X against the time step. Then I will extract the reaction. So I go to next, it says, okay, perform your selection. So I select the top node here, next, and I call it U. Now, as you can see in the new version, you can choose what happens if you select more than one node. Now, in this case, it is one node, so it's the same, but you can choose between add, average, max, minimum, or keep multiple results. Now, in this case, we want to add everything. So finish. This one is the displacement versus the time step. Now, we do the same for the reaction forces. So once again, here, extract. On nodes, we choose reaction force along the x direction. Next. Now we choose all the nodes at the bottom line, so the fixed ones. Next. Now here it is important to keep add. If we add, we sum all the results, so we have the total reaction. Otherwise, you can choose something different, but in this case, we want to add them. Let's call it F. Finish. And this one is the evolution of the base shear along the time step. Now, of course, you can go here, you have all the values, you can copy paste them to Excel as I did before. And these one are the values for the displacement and the reaction. And here I just copy them, and here I just change the sign, because in this case I want the force. So this is the output that we obtain, which is quite good with the experimental results. We just need to put probably some more plasticity, but in this case I just used those values, which is fine. You can try to play with the plasticity values to check if you can get better results here. So this is our example. So you can see that it's quite extremely easy to do this kind of modeling. Probably the most difficult part was the CAD modeling of the microstructure. But we are working actually on a plugin that will allow you to create all the micromodel from in an automatic fashion. So we will present it in we are actually now doing some tests on it. And in the future version, we will have also this feature available in STKO. So the entire micromodeling can be done just choosing the type of masonry. You can apply micromodeling onto the entire surface. So with this example, I'm done. So if you have some question, let me open this one. If you have any question, please, I can answer. let me just remove the full screen so I can see what happens here. Is there anyone that has questions? Yeah. Yes, the video is recorded. I missed one part and maybe you already said it. I would like to know if I can perform nonlinear time history analysis. Of course you can. In this case, I just used a static analysis, but to perform a nonlinear time history analysis is extremely simple. Let me just give you an example. Now, we are not going to do it now because I don't have the actually a ground motion to apply to it, but it is extremely simple. So if you go under the preprocessor, as you can see here under the analysis, I have chosen the static one. To perform a nonlinear time history analysis is extremely simple. You just need to go under here to choose transient, and then you need to change a couple of things. For example, the integrator. By default is the central difference, which is explicit. So if you are not expert of explicit method, let's change it. And you can use, for example, the numark method. You choose the numark parameter that you want. By default, it was 0.5, 0.25. And you can choose the number of increments. And this time, the time step, which is the real time step. So in this case, you just set up a dynamic analysis. Of course, you need to change something in the loads. For example, in this case, my horizontal load was an applied displacement. In your case, will not be like this. Will be a uniform excitation. So how do you do a uniform excitation? Well, you can first go under definition. You can add a time series of type path. Here on the path, you can copy paste. For example, you can go under, not under constant, but under non-constant. You can copy paste here your accelerations and here the time step, okay? So you have this extra time series, and now instead of creating this impulse displacement, you can create a uniform excitation in the analysis step, like this one. You go under pattern, add pattern, uniform excitation, and here you choose the direction, and you choose the time series for the acceleration. And basically you're done with nonlinear time history analysis. Okay, let me go back to the questions. Okay, do you have any suggestion for the equivalent continuum for Masonry? Particularly, is there any material that can be used with a simple mesh? Since I was wondering if there is a material that can be used to model together Masonry and Mortar. Yes, actually, how can be added the gap links? Oh, just a second. Let me just answer to Raffaele De Risi. Of course, you can use the same material model that we have used for the microstructural components for the entire Masonry. The only problem is that that material model is isotropic. While if you want to model the entire Masonry as a continuum, you have to consider the fact that it will be orthotropic. Now, fortunately, we are writing a paper right now using a material adapter formulated by Professor Sergio Ye and Luca Pelà, which basically can convert any isotropic constitutive model into an orthotropic one. And we are going to add it very soon. So it will be available in STKO very soon. A guy is just writing his thesis on it, and then we will add it. And also the comparisons are quite good. We've just done some comparison. I can send you some material. So next question, how can be added gap links? For gap links, do you mean gaps between, just a second. Let me answer to Jose Poveda. First of all, what do you mean for gap links? Do you mean probably connections between the masonry wall and I don't know, some boundary beams? Trying to model self-centering masonry. No, I mean gap links inside the constitutive model. So I don't understand where you want to apply these gap links. Can you send me any? let's do this. Try to write on the forum, and if you can send some reference on how to do this one, so we can see if we can implement it, okay? So next question, Rodrigo Amezcua. Is the employee constitutive model available in OpenSys versions? No, at the moment, no. The constitutive model that we use now, so the damaged TC3D, is available in our own version of OpenSys. So the one that you have in the STKO plus OpenSys version. Why? Because we are writing some paper on it, but we will add it to the global OpenSys quite soon. Actually, not inside the source code, but as an external DLL. Okay. So if you want to use it now, actually, you have to use our own version of OpenSys. Otherwise, there is a quite similar constitutive model, which is the damaged 2P. Unfortunately, it is not. It is quite similar, but it is not implex, so pay attention with the convergency issue. So next question, I had for Raffaele that you're not, then Huawei Mate 10 Pro. Let me, yeah, it is available, but only outside of Italy. Yeah, of course, this is another problem, of course. If you are in Italy or if you belong to an Italian institution, you cannot download STKO plus OpenSys because in Italy there is a restriction. There is another software house that has the exclusivity of distributing OpenSys. But actually we are changing now because we have talked with the Berkeley and they said that we can redistribute it through some universities. So we are working on it actually. But in any case, very soon it will be available as an external DLL. Just another question. Okay, thank you. I don't understand this question here. I had for a fact that you're not simplifying much. With the index, it is very fast. Yeah, it is very fast because actually the implex method, always the convergence is guaranteed. Now, actually, I don't want to go into the details of the implex because you may have in certain cases also with the implex method some convergence problem, but it will be only at the end of the analysis. For example, if you damage the entire masonry in compression and your vertical load is higher than the residual strength, of course, even if you're using the implex method, you will never reach convergence just because there is no equilibrium point. But those are only the few cases in which the implex is not cannot guarantee the convergence. And of course, with the implex method, you have to pay attention because the time step should be sufficiently small. Not so small as in the pure explicit methods, but it should be small. So of course, there is a drawback in the implex. But if you understand how it works and you understand how the time step should be, you can get quite fast analysis with the implex method. I see a drawing here. Probably someone is drawing. No? Okay. Is there any other question? Probably we are going to organize. Okay. How long is an analysis of a building? Well, it depends. It depends because, for example, this analysis here, using just one processor, it takes something like from 8 to 10 minutes. Actually, I have another analysis that lasts like 15 minutes using 8 processors. Let me show you. Yeah, of course. You can use multiprocessors. I didn't talk about it, but let me show you for what analysis I used multiprocessing. Let me give you an example. Let me close this one. Let's say you want to do multiprocessor analysis of this thing here. You can just go under mesh, and here you have the partition. Now, in my case, I have OpenSys here. Actually, I have many versions of OpenSys. I have the one that is shipped with STKO, then some other manual ones, and this one is an OpenSys MP. Unfortunately, we cannot redistribute it now because we started with the sequential OpenSys because OpenSys MP should be compiled directly on your machines. So it takes some time, but we will try to give you instruction on how to build the parallel OpenSys in future webinars. But it's extremely easy to use OpenSys MP because here, let's say this one is a very huge model. You can go under partition and choose the number of partitions that you want. For example, in my computer here, I have 8 processors. So you choose 8, you click partition, and as you can see here, STKO subdivides the entire mesh in the number of partitions that you want. Okay, so you say done. Now, when you have partitioned your mesh, you just need to do very few changes to make the analysis run in parallel. Basically, in the analysis, you should do 2 changes. The first one should be the number. The number should be the parallel one. There is only one, so you cannot make any error here. Just choose the parallel RCM key. Okay. And the last change should be done in the system because you need to choose the maps or the parallel profile SPD. But unfortunately, the SPD is only for symmetric and positive definite matrices. So in your case, you should choose the maps. So when you're done changing the number and the system, and you partition your mesh, you can do your analysis in parallel. And it is quite efficient. Of course, don't think that if you have many processors, your analysis will be always faster. It depends. You need a very large model. For example, I've seen that if I have good speed ups, I need at least something like 1,000 or 2,000 elements on each processor. So, for example, here I have 6,000 elements. I can get improvements if I take, let's say, 4 partition, but not more, because with 4 partition, I already have less than 2,000 elements per processor. Okay. So of course you can do it. I will do it in a future version because I need to explain something more about the parallel OpenSys, how to compile it, what you need to change. Did you do a comparison with the equation from codes, maximum brief? No, actually, in this example, I didn't do any comparison, but I can do it. It can be an example for a next webinar, of course. Yeah, Corrado did something. Corrado did something, and probably we can do it in a future webinar. Yeah, of course. Corrado did a lot of comparisons, and they were quite good. Actually, what I want to do about Masonry in future webinars are the out-of-plane, how to model the out-of-plane either with solids or with shells, because unfortunately now we don't have time now, and how to do this comparison with national and international codes, and how to do parallel analysis, because when you talk about a micromodeling, of course you have all the accuracy, all those stuff, but you need to explain how to obtain reasonable result in a reasonable amount of time. So the implex plays a role because it avoids all the iterations. But then, of course, you need to use parallel processing. So these are the future webinars about Masonry micromodeling. And probably the last one will be on how to use micromodeling to predict the material property for equivalent continuum models, what Professor Derisi was saying before. Because now we have the continuum isotropic model, the orthotropic adapter, and then we have a procedure to use a representative volume element and to get from these representative volume elements all the equivalent strength in the different directions. So this one will be the last topic that we're going to cover in this series of webinars. Is it possible to request webinar? Yes, of course. Of course, and if you have any question, please either write on the forum, it will be better. We have a forum on our website. If you can use it, it will be nice to request special topics, or you can just send us an email. We are glad if you give us feedback so we can prepare topics on what you really want. Of course you can. Actually, since we are scheduling a lot of webinars now, almost 2 every month, so please write an email very soon so we can schedule it. Okay? Is there any other question? Oh, thank you to everyone. So, if there is no other question, we can close it, and as I told you, if you have any idea on future webinars, something that you would like to deal with, just write an email very soon, because we are actually in the phase of scheduling something like 2 or 3 webinars every month. So, of course, it's fine. So let me stop sharing. Oh. Thank you to everyone, guys. Okay. Bye.